that, so I have not listed the collaborators in this because that would take the whole screen, but hopefully we'll see it as we go along. So what I'll do is I'll show you some results for flow modeling using some high performance computing. And I'm not going to dwell too much on the equations and the algorithms, but suffices to say, these are some sample flow equations. So if you want to model incompressible flows, then there's the famous continuity equation, which is the mass balance. Then you have the force balance, so that's the momentum equation. And then you'll have to assume some constitutive laws. In this case, we restrict ourselves to Newtonian fluids. And then, of course, boundary conditions and initial conditions. And we remember that these are unsteady equations. They are nonlinear. They are coupled in the form of partial differential equations. So they are not very trivial to solve. So we usually use some numerical method. In this case, I will show you some results from using finite element formulation. So these are stabilized methods. The green terms are essentially the Galerkin terms, but one knows that Galerkin methods produce instabilities. So we usually stabilize them. And the red terms are essentially the least square terms on the momentum equation. And the blue term is the least square term on the stabilization term for the continuity equation. Then we can incorporate the boundary conditions, both Dirichlet and the Neumann type, but I'm not going to spend time on that. I'll just say that it's not just enough to model these equations. You also have to have a way to compute them quick, very fast, to do large scale calculations. So we've spent some time on parallelizing these codes, both on shared memory and distributed memory. So often one uses a method called domain partitioning, where if you have unstructured grids, then you try to make small subdomains of elements that are very close to each other, so they are neighbors, because communications are very difficult on a cluster. So you employ three data structures: nodes, elements, and equations, and information has to be passed between these. So just to give you an idea, if you are using a finite element method, then the nodal coordinates and the unknowns are stored at nodes, but then you have to carry out integration of the equations. Those are carried out at the elemental level. So you need information between elements and nodes. But equations are, the global assembly of these elements. So you need another data structure at the equation level. So you will have to pass information between nodes, elements, and equations. And any good fast method should be able to cut through these different levels of data structures. So we use these nonlinear equations are solved using a solver based on the GMRES, the generalized minimal residual method. It's an iterative method. And often we use diagonal preconditioners. Sometimes we use block diagonals, and if that doesn't work, very, very reluctantly, we use incomplete LU decomposition. But usually diagonal preconditioners are enough if you use good stabilized methods. And information is passed using the message passing libraries. So these would result in fairly reasonable speed ups. So on the x-axis, you see the number of cores. The y-axis is how much the code speeds up. So if you had an ideal situation, you would see the red line, that the more the number of processors you use, the faster you get. But that very rarely happens. So for example, if you use a small mesh M1, which is just about 16 million equations, then as you get to a large number of cores, the overheads are so large, you don't get very good speed up. And maybe beyond 200 cores, it is not a good idea to use a larger number of cores, because as you see, the curve is actually saturated. Okay. But as you go to larger meshes, and in this case, I want to give you an example of mesh M5, which is about 370 million equations. So then you get a very good speed up and you can use a large number of cores. So every problem that you do, I think it's a good idea to do this study and realize how many cores are enough for you. Okay, having set this up, I thought I'll just talk about some of the problems that we have done in the past. So I'll give you some examples from some complicated flows, at least complicated from my perspective. So we'll look at a cricket ball, maybe something about a badminton shuttlecock that should excite you. It also involves fluid structure interaction. Then some recent work we have done on frisbees, on flow past wings, which is actually my parent department, aerospace engineering. We worked on design of some parachutes. So there are two kinds of parachutes: the round canopy and the ram air parachutes. So how to design good parachutes for nice performance. And I'll show you some examples, time permitting, from air intakes. So these are actually these ducts from which the aircraft ingests air, and then this air is taken to the engine where the combustion takes place. So the idea is, how do these intakes perform for different throttle settings within the engine? So there would be very high pressure and temperature inside the engine, and these intakes are designed so that the flow is in equilibrium. So I'll talk about that. Okay, so let's first talk about the cricket ball. Uh, may I just ask if I'm audible and everything is clear so far? Maybe Anurag, you can help me.
Yes, sir. It's audible and everything is clear, sir.
Excellent, excellent. So let's go ahead with first the cricket ball. So here I bring your attention to just flow past a sphere, a smooth sphere. And if one looks at the drag force on a smooth sphere, you can plot it with Reynolds number. So Reynolds number is defined over here. So if I take a sphere of diameter d, then rho and mu are fluid properties. So let's say we focus on air. Then Reynolds number is directly proportional to the speed if you fix everything else. So what people have found is, if you look at the red line is the drag force. So the drag increases roughly square of speed. So it's a quadratic curve. And till the boundary layer remains laminar, the drag keeps increasing quadratically. And then at some point, it just reduces, it falls down. So the surprising thing is, if you increase the speed till some point, the drag increases. And if you increase it a little bit, then actually the drag force goes down. The boundary layer is going from a laminar to a turbulent state. And that's why you see a very large. So it remains constant in the laminar regime, and it also remains kind of constant in the turbulent regime. And then in between, it goes through a drastic change. So we subdivide the flow regimes into subcritical, where the boundary layer is completely laminar. You can see here a laminar boundary layer just separates at the shoulder. And then it goes through this transition to a turbulent state. And a turbulent boundary layer is shown in this little view graph here. So you can see the disturbances, heavy mixing. But finally, the boundary layer separates far downstream, and that's why the drag is low. Okay. Okay, so that's a smooth sphere, and you can actually look at it in flow visualization. So if you take a sphere of black color and put dye on it, so oil mixed with dye, and you start the flow in the wind tunnel, then all this oil will get pushed downstream, but the flow separates near the shoulder. So you can see the oil piles up here. So you get a black color just before the separation point and little whitish after the separation point. So this can be used to identify the laminar separation. So this was done in the wind tunnel here at Kanpur. And the separation point is about 80 degree. On the other hand, when the boundary layer becomes turbulent, so you get the separation point moves downstream, a little bit downstream of the shoulder at about 105 degrees. So the oil collects here, but something magical happens. The flow again reattaches. So you can see the flow has piled up, the oil has piled up here. The black region means that there is no oil there, which means the flow has actually reattached. So the cartoon here shows there's a laminar separation. There's a laminar separation bubble. So the flow attaches at this point, and then it finally separates as a turbulent boundary layer downstream. Okay. So that red line is the final turbulent separation, and it shows you the transition. Now, this was for a smooth body, and Professor Achenbach did these experiments by roughening the surface of a sphere. And what he found is that as you increase the surface roughness, this transition point where the boundary layer goes from a laminar to a turbulent state, that shifts to a smaller Reynolds number. But of course, the drag, which was very small for a smooth sphere, now actually becomes a little bit larger as you increase the roughness. So the message is that if you want to reduce the drag at a large Reynolds number for a sphere, you could possibly try making it rough so that the transition occurs a little bit early. But of course, the final drag would be a little bit larger compared to a smooth sphere. Um, Now, this is what is used for a golf ball. If you know, the golf ball has dimples on it. So the idea is, if a golf ball is operating at, let's say, something like a speed corresponding to Reynolds number of 10 to the fifth, the boundary layer there would be actually laminar, so the drag would be large. But if you can make it rough, then perhaps you would operate at this point. So you would have a smaller drag coefficient, and perhaps the ball will go much further if you hit a shot compared to if it was laminar. So that's why golf balls are made uh, kind of rough. They have dimples on them so that the boundary layer is turbulent. Now the drag crisis takes place for a smooth sphere at about 5 into 10 to the fifth, that kind of a Reynolds number. But cricket balls, golf balls, they work at around 10 to the fifth. That's why roughness is very important, and that's what I want to show you. So let's go to this traditional, design of balls. So if you look at a typical cricket ball, it has two seams. In fact, I have a cricket ball here with me. I don't know if you can see it. So there is a seam on it, a primary seam, and there's a secondary seam. So that's a 4-piece cricket ball. So we are going to ignore the secondary seam. The diameter is about 72 mm. The mass is about 150 grams. And typically it operates at a Reynolds number of 10 to the fifth. In an entirely different continent, you have the baseball. Magically, the diameter is still about the same, 72 mm. The mass is about the same, 150 grams. The baseball is thrown underarm, so it has a little bit higher Reynolds number. So that's about 1.5 into 10 to the fifth. But you can see two different projectiles from two different continents and very, very similar geometries and mass. Golf ball is a lot smaller, about 42 millimeters, and it has a much smaller mass, about 46 grams. But because it flies at much larger speed, the Reynolds number is still the same. So about 2 into 10 to the fifth. Okay, so we remember that the drag crisis or the transition of the boundary layer for a smooth sphere takes place at about 5 into 10 to the fifth, but for these rough bodies, they have to take place at about 10 to the fifth. We'll remember that. Okay, so here's a cricket ball. So you are a batter, I am a bowler, and you want to hit my deliveries, and I want to deceive you. So one way of deceiving the batter is you bowl very quick. The batter has very little reaction time, so they could miss the delivery. The other is by lateral movement of the ball. So you can do spin bowling. So spin you can have through the air, movement through the air through Magnus effect, but we are not going to talk about it. You can also have a drift by simply the dynamics. So you spin the ball, it lands on the surface, on the pitch, and then it moves. We are not going to talk about that, although that's very effective. Then you have something called seam bowling, like what Venkatesh Prasad did very effectively, my generation bowler. So here the seam is held vertical, the ball hits the pitch, and because the ball is not perfect, the impact is not exactly at the seam. So the ball could go either to the leg or to the off, and it's very difficult to detect. So um, we are not going to talk about the seam bowling as well. Today we are going to, yeah.
त्याच्यात डीवर माझी सो करून
Yeah, is it okay? Shall I go ahead?
Yeah, sir. You can
Okay, okay. So we are going to talk about swing bowling, where the bowler holds the seam vertically, but then the seam is pointed towards a slip, either the leg slip or the off slip, and the ball will move in one of the directions. I'll show you. Okay, and you can have many kinds of deliveries: in swing, out swing, reverse swing. So I'll explain you in a moment, and we are going to analyze the fluid mechanics of this bowling. So here's an example. So I am a bowler. I bowl from the stumps. I could bowl either over the wicket or the other way. So the important thing is I could have an in swing or an out swing. So diagrams are shown here. Out swing is obviously the ball pitches and then moves outside, or the in swing is the ball pitches from out and moves in. So that's the classification for in versus out swing. But for us, the important thing is the conventional swing and the reverse swing. So if you see, typically what happens, the bowler bowls, the batter watches, and if the ball moves in the direction of the seam, then that's called conventional swing. And if the bowler bowls and the ball moves in the direction opposite to the direction of seam, that is called reverse swing. So I go back to the previous picture. You see, in both in swing and out swing, the ball is moving in the direction of seam. Okay. In the outswing case, the seam is pointing towards the offside for a right-handed batter, and in the in swing, it's pointing towards the leg for an offside batter. And in both cases, it moves in the direction of seam. So this is what usually happens. So the batter is watching the bowler very carefully, sees how they hold the ball, and they expect that the ball will move in the direction of seam. But some bowlers can be very deceptive. They will hold the ball in a manner that the batter thinks it will move in the direction of the seam, but it moves the other way. So that's called the reverse swing. So one question is, why does swing happen and why does reverse swing happen? And second question is, often we hear commentators saying that the ball is old and now it can reverse. So does that mean that a new ball cannot reverse swing? So these are some of the questions that some of us had as aerodynamicists, and the idea of this research was to address those questions. So the first thing we did was some experiments. So we set this up in the National Wind Tunnel facility. So it's a very nice facility. You can go all the way up to 80 meters per second, although that's not needed for cricket. In cricket, the maximum bowling speed is about 155 kilometers per hour. So you can take a cricket ball, mount it on a sting, an example is shown here. So you can change the seam angle by mounting it, and you can change the speed and then collect data. So we did that, and we also did CFD. So shown here are some examples of AutoCAD models that we made for CFD: a smooth sphere, then a sphere with one trip, a sphere with three trips, and then the last image is for actually a example of a cricket ball, okay, with five trips. Okay, so you do the meshing. So shown here is surface mesh for a cricket ball. So you have to resolve the seam, unstructured mesh far away, a nice structured mesh close to the cricket ball. So first you do some calculations for a smooth sphere, just to make sure that you can capture the details of the flow and the drag crisis. So you can see at low Reynolds number about 10 to the fourth, you get these shear layer instabilities, but the wake is quite wide. The separation is very close to the shoulder. But if you go to large Reynolds number, then the separation moves downstream and you get a narrow wake. So we are able to capture the turbulent boundary layer and its transition. So these are some view graphs which show the pressure distribution. And you can see at large Reynolds number, you get a very high suction, which is very typical of a turbulent boundary layer. Okay, so let's come back to the cricket ball, and I will show you the combined CFD and experimental result. So the way the experiment is set up, you have already seen the mounting. So there's a cricket ball which is facing us. The flow is going into the screen, okay, which means you can imagine the ball is coming towards us. So you are the batter, the ball is coming to you. Right now, this ball is facing, if you are a right-handed batter, the ball is facing towards the off slip. So if the ball moves towards the off slip, that would be conventional swing. If it moves towards the leg slip, that would be reverse swing. So we'll call the positive force as the conventional swing and the negative force as the reverse swing. Okay. Of course, we are going to ignore the secondary seam of the ball. There will also be a lift on the ball, but we will ignore that. Okay. Although that's very important, but not for this talk where we are mostly interested in swing and reverse swing. Okay, so I repeat, the experiment is the following. We'll put the ball at a certain angle. Maybe in this case, it is a 30-degree seam angle. We'll change the flow speed from a low speed to a high speed. And then we are going to monitor the drag force and the swing force. A positive swing force means we have conventional swing. A negative swing force, we have reverse swing. So the question we are asking is, A, how does the swing force change with speed? And B, can we get reverse swing for a brand new cricket ball, such as the one mounted in the tunnel? Okay, so these are the results that we saw from the wind tunnel test. There are many models here. We made spheres, synthetic spheres with trips. So we'll ignore all that. Let's just look at the cricket ball, which is the blue line. So please look at the lower figure. Okay, that's the swing. So it turns out that if the Reynolds number is very small, that means the speed is very small, then the seam doesn't make a difference, and you get no force, no swing force. Then as the speed increases, the swing increases, the swing coefficient, force coefficient increases, it saturates, and then at some Reynolds number, you start getting reverse swing all of a sudden. Okay, so which means a new cricket ball can reverse swing. And same thing happens with the drag, so it reduces with speed, and at some point it just comes down drastically when the boundary layer is completely turbulent, and you get a lower drag. What is the phenomena? I have tried to list it in these cartoons. So let's first look at the conventional swing, and then we will look at the reverse swing. So in the conventional swing, there's this seam which makes the boundary layer kind of trip, and it becomes turbulent. So the separation point is downstream. On the non-seam side, the flow, the ball is shiny, so the boundary layer remains laminar. So you have laminar separation on one side, turbulent on the other. So more suction on the seam side, so you get force as shown in this arrow, and that's the conventional swing. As you increase the speed, now it turns out that even for a smooth side, the boundary layer is going to become turbulent. Okay, so if your speed is large enough, so your boundary layer is now turbulent here. But on the seam side, because the boundary layer is affected by this seam, so the turbulence is kind of a forced turbulence. And people have shown that if you have the natural transition versus a forced transition, then the separation is a little bit more downstream for the natural transition compared to the force. And therefore now you get this reverse swing, but it is much smaller. The suction here is, you can see the coefficient here is almost of the order of minus 0.15, where if it is swing, it is of the order of 0.35. Okay. So Anurag, I just wanted to check that is everything okay? Shall I proceed further?
Yes, sir. Everything is okay.
Okay, okay, great. Okay, so I wanted to show you that we did experiments. So the second panel, sorry, the third panel that you see here is from the oil flow visualization. This is at a Reynolds number of 10 to the fifth. So you get this very nice flow structure here, which is reminiscent of the laminar separation bubble. And if you look at the CFD, these are the first two columns, just different orientations. So the blue color shows the pressure suction that you get, and you can see the CFD, actually the LES studies. They very nicely reproduce what is seen in the experiments, and in fact, this appeared on the cover page of JFM if you are interested in this article. Okay, the CFD actually told us a little bit more than the experiments, and I want to highlight that. So if you please look at this second picture on the right. So that's the swing coefficient versus Reynolds number. The solid lines are the cricket ball. So you can see the cricket ball in the red line, and the sphere with 5 trips is the experiments for the smooth sphere with 5 trips. And the CFD data is in triangle. So we get very good agreement. What the CFD showed is that actually the boundary layer doesn't become turbulent for all swing cases. Initially, the boundary layer is laminar, it just gets delayed, the separation gets delayed, and eventually it becomes turbulent. So there are two subdivisions in the swing. First, the boundary layer is laminar, it is just delayed separation, and then finally it becomes turbulent. So this was an extra thing that CFD was able to show. I'm going to skip this. Something very interesting also came out from the CFD calculations. And see what happens when you have an airplane. The airplane produces lift because of suction on the upper surface of the wing and a high pressure on the lower surface. But at the wingtips, you get this leakage of flow. And they form these so-called wingtip vortices, which are visualized here. Now, in a cricket ball, we have the same thing. So if I bring your attention back here, so here is a cricket ball. It is moving, let's say, towards the left, okay, towards the batter who is on the left, and you get high suction on the upper surface, a little bit high pressure on the lower surface, and one would expect that the flow would leak from high pressure to low pressure on the sides. So we were expecting that just like in an aircraft you get these wingtip vortices, you should get wingtip vortices in a cricket ball also. So we visualized it, and to our surprise, we found that in fact there are these wingtip vortices in a cricket ball. Okay, and in fact, for shift swing and reverse swing, you could get a very interesting polarity, but I'm not going to give you the details. You can look it up in this paper. And there is something that came out of the CFD study. So you can also get the trajectory of a cricket ball. Once you know the force coefficient, you can integrate this equation and then find out when the ball is swinging and when it is reverse swinging. Again, you can look at this paper if you are interested. Um, we also did some experiments to figure out what happens if you have an old cricket ball. So here is a brand new cricket ball. You rough one of these sides, and then you can have a completely rough cricket ball. So this is called contrast swing. You must have seen that many players, they will shine the cricket ball on their trousers. So the team will decide to keep one side shiny, the other side will become rough, and actually it has implications in the swing. So I want to just give you one example. So if you take a ball like this, where the seam side is shiny, but the non-seam side is rough, then actually you can get reverse swing at even 50 kilometers per hour. Okay, the red curve is for a brand new ball, where you get reverse swing at about 150 kilometers per hour. But if you had a old ball and you engineer it well as a team, then you could get reverse swing even at 50, or which means spinners like Kumble, who throw a little bit quick, they can combine swing and spin and get very. So Jadeja does that. He is very quick, and he can actually an old if he gets an old ball, then he can combine spin and swing and produce some really magic. Okay, we now move on to the second part of this presentation, which is about a shuttlecock. So we've been interested in badminton shuttlecocks. I play badminton myself, and one of the questions that we have been addressing is what is the difference between a duck feather shuttlecock and uh, a, a nylon shuttlecock. So as you might be aware, these are very light. A shuttlecock varies only about 5 grams because it's made of these natural duck feathers. They are bones actually and hollow, so they are extremely light. And the fastest smash recorded in badminton, which the record is held by Indians, it's about 550 kilometers per hour. You can see it's really quick. Okay. So it is very difficult to design a nylon shuttlecock. It should have the same dimensions. It should have the same center of gravity, and it should have the same aerodynamic performance, which means the rolling moment and the drag force. So why are these different? So I asked one of my very bright students several years ago to make these models. So they made these AutoCAD models for a nylon shuttlecock, a feather shuttlecock, and then I asked them to make also a shuttlecock which has no gaps in them. So it's just a frustum of a cone, but hollow inside. So they put a mesh around it, did some CFD, and this is what they got: nylon feather and the one with no gaps. So of course this is a bluff body, so it has a very large wake, and you can see the wake of the other two. And when they compared the drag coefficients, this was an eye opener. So the gapless shuttle has the smallest gap. As an aerospace engineer, I was very surprised. I was hoping that the gapless shuttle is a bluff body; it would have the largest gap. So it turns out that the gaps, they contribute to the drag. Then the feather shuttle has somewhere in between, and the nylon shuttle had the largest drag. So this was a little bit of a surprise. A, why does the gapless shuttle have the smallest drag? And how come the synthetic shuttle or the nylon shuttle has a drag different than the feather shuttle? We use the shuttles from Yonex, and Yonex should have probably tuned them so that the drag is same. So this why are they different? This bothered us. So we did some wind tunnel experiments. Back to the wind tunnel. So a shuttlecock is mounted on a sting. You turn on the flow, measure the force on the shuttlecock. And I would like you to look at these two lines, the red lines. So first, the duck feather shuttlecock. Those are the hollow circles. And you will see the drag coefficient remains almost virtually constant with speed. So the top x-axis is the speed. At the lower axis, you see the corresponding Reynolds number. Okay. So you'll see the duck feather retains its shape, just compresses a little bit, but more or less the drag is same. On the other hand, if you look at the nylon shuttlecock, it has a circular section, but then as you increase the speed, this nylon skirt gets deformed. It in fact buckles and takes this squarish cross section, and therefore it offers less resistance and the drag reduces. Okay. So Yonex is actually very smart. They tuned the shuttle, the nylon shuttle, because the drag is going to decrease to about 100 kilometers per hour. So at 100 kilometers per hour, the nylon and the duck feather shuttlecock have the same drag, but the drag is high at low speeds and much small at high speeds. Okay. So the question is, why does this happen? And we figured that it's because of the pressure difference between the inside and the outside. So there are some papers that have come out from our group. You can look at them if you are interested. Can we look at this deformation from a fluid structure interaction point of view? So some students took up this challenge. They did the fluid structure interaction study. So model the structure of the shuttlecock, the nylon shuttlecock here, and you can see the details in this little zoomed in. So this is one thing, and then we would make a mesh for the fluids and then couple the two. Okay? And when this whole thing worked, what we found is that at very low speeds, this is the pressure distribution on the shuttlecock. You get a very nice undeformed shape. But if you go to a little bit higher speeds, then the pressure loading on the shuttlecock causes it to buckle, and you can see almost a square cross section. So this spontaneously came out of the fluid structure interaction calculations. Okay. If you plot the drag coefficient with speed, then it turns out, if you look at the red line, the drag coefficient reduces with speed, and at some point here, 40 meters per second, the shuttlecock actually buckles, the drag comes down very rapidly. Then in fact, the skirt starts vibrating, and then if you increase the speed more, it vibrates, and there's a traveling wave in the circumferential direction. So these are some pictures of the shuttlecock. You can imagine the shuttlecock is facing you. So imagine a shuttlecock facing you with the cork away from you, and you are looking at it, and the colors indicate the deformation in millimeters. So at 30 meters per second, the deformation is very small. Then you can see at about 40.5 meters per second, the shuttlecock buckles. So from a circle, it goes to a square cross section. The deformation is large at the edges. You can see this red color. And then you get vibrations and finally a traveling wave. Okay, we compared the drag coefficient from these FSI simulations. And you see the comparison here, fairly good comparison, and that's the buckling. And see if we can tune it to behave more like a duck feather shuttlecock. Okay. Okay, we have done studies for other sports equipment, and you can look at this paper in Physics of Fluids at 2019. So many equipments, and we were able to put the drag coefficient for all of them on one table. Okay, I just present to you some more results for a frisbee we have done recently. So we are interested in the transition. So this is flow on a frisbee at 0 and a 10-degree angle of attack. It has a very nice flow structure. You can see the again a laminar separation bubble transition to turbulence. Okay, so this is the laminar separation bubble on the frisbee. And you get these very nice wingtip vortices because when the frisbee flies, it acts like a wing. So the flow leaks from the bottom to the top and so on. Okay, maybe for lack of time, I will skip all this and maybe I show you some things for wings and airfoils. I have about 15 minutes. So these are smoke flow visualizations for an airfoil. So at very low angles of attack, you get an attached flow. At large angles of attack, you get separated flows, and then the lift can come down. So that's called a stall. So we did some calculations for an Epler airfoil, and to cut a long story short, if you do 2D calculations, you don't see a stall at all. Okay, and these are some 3D results. But if you do a 3D calculation, which is the blue line, then you are able to see the stall. So the flows are very different, the 2D and 3D flows. So just to show you that you have to do 3D calculations to generate reasonable answers. Okay, so we have tried to figure out how the transition takes place on an airfoil. So at very low Reynolds number, you get just the regular two-dimensional vortex shedding, then you get these 3D structures, and finally you get a turbulent boundary layer, which is shown in these pictures. Okay, how does these wingtip vortices that I just showed you interact with the vortex shedding? So we did calculations for a finite wing, and what we found is that this wingtip vortex can interact with this vortex shedding and produce these very interesting flow structures. So this is an airfoil, an end-to-end airfoil where there is no finiteness, so there is no wingtip vortex. So the flow is three-dimensional but very nice, regular. But the moment you have this wingtip vortex, it interacts with these vortices, and you get these very interesting flow structures. So recently we found out that it can give rise to some very surprising deviation from the conventional airfoil theories. So I will not bore you with the details, but if you are interested, you can look at our work in JFM. Okay, some animations just to show you that how these linkages they travel and produce these streamwise vortices which can affect the flow. Some work that we did on parachutes. So here is a person trying to fly a parachute, and the idea is to design these flexible flying wings so that you have good performance. So normally this parachute is packed inside a backpack. So the air trooper, he jumps out of an airplane, pulls some straps, and then this parachute inflates. So the inflation depends on these cuts. So the air goes through these cuts and fills this parachute and makes it a wing. So the idea is if this cut is very tiny, then the parachute won't fill up and this guy will have a bad time, just fall on the ground. But if this is too large, the cut is too large, then the aerodynamic performance of the parachute is not good. So the idea is to design a parachute with the optimal cut at the leading edge so that the inflation time is small and yet the performance is high. So we parameterize this with some theta cut and an x cut, these two parameters, and try to find out what is the optimal cut angle. So some CFD calculations were carried out first for a airfoil without a cut, then with a cut, and you figure out what is the lift and drag penalty that you get. So you design it. So I've listed out some cases. The values are not important, just to let you know that this can help you optimize the cut. Then, of course, you do 3D calculations and you help design a parachute. Okay, I show you some examples of fluid structure interaction. So if we are interested, let's say in the shuttlecock case, then the fluid forces act on the structure and the structure deforms, and you want to look at that. So here is a benchmark problem from Turek and Ron. So there is this splitter plate behind a cylinder and it vibrates under the action of fluid forces. Um, so the important thing here is you are solving for three things: the fluid, the structure, and then the mesh. Okay, so there are three solvers running one after the other. So you calculate the fluid flow, transfer those forces to the structure gets deformed, and then once the structure is deformed, then you want to make the mesh for the deformed structure. So we assume that the mesh itself is like a rubber, so it's like a domain full of rubber, and the points are deformed on it by applying some displacement on the boundaries. So the mesh also has to be deformed along with the calculation. So just to show you why we are interested in this, so this is a flow around multiple rigid filaments. You can see a very nice flow. So there is a flow in the near wake, and then it reorganizes itself into these nice vortices far away. And now the question you ask is, what if these filaments are flexible and they could vibrate? And if you allowed them to vibrate, then this is what happens. Okay, they vibrate sometimes in the first Euler-Bernoulli mode, sometimes in the second or third. Some of them are vibrating in phase, others are vibrating out of phase. And you can see the flow. I mean, all that nice organization is now lost. Okay, so very complicated. So we thought before we jump on this problem, maybe we should look at just one filament and see if we can simulate that. So the idea is to just look at one filament. So here is a flow for a single cylinder without the plate and then with plate, and of course it reduces the vortex shedding. Um, so if we have the structure, then it can get excited into these different modes: the first mode, the second bending mode, the third bending mode. But the fluid has a frequency. So if the vortex shedding takes place at this frequency, then perhaps at different flow velocities, we can get excitation of different modes: the first mode, the second mode, and third mode. So some calculations were done, and indeed, you can get first excitation with first mode, then with the second mode, and then some higher modes like the third modes. Okay. So you can get very interesting results here. You can get effect of initial conditions where the amplitude of vibration can depend on whether you are increasing the speed or reducing the speed. The flow is very complicated, but we can also try to, by choosing appropriate non-dimensional parameters, we can group the vortex shedding into some regimes. So I'm sorry I don't have the time to go into the details, but if you are interested, you can look at some of our papers and look at some details. So what happens if you have two plates? So here is an example of two plates, and something very interesting happens. So initially they vibrate out of phase, and then finally they can vibrate in phase. So that's what is shown in this picture. This is the initial simulation, the initial part of the simulation, and the final part where they are vibrating in phase. We've done some fluid structure interaction for balloons. So here is an example of a balloon inflation. So this fluid is pumped in through this straw, trying to inflate this large spherical balloon. And because of the added mass effect, you can see it oscillates a little bit. We can also model the flow inside it, so you get these very nice toroidal vortices. Then if you want to deflate it, it can be deflated, or if you put a small defect in it, there could be fracture. So we have a model for the fracture of rubber. In fact, this is how the fracture proceeds. You can see. Okay, the last problem that I want to show you is before I sign off is flows in intakes, aircraft intakes. So typically what happens if you have these fighter airplanes, uh, just like our human body, we have two nostrils. So the flow comes in through the nose and then it feeds the lungs. So there is one trachea, so one air windpipe. So these two nostrils will go and feed the windpipe. So in the aircraft, it is two air intakes feeding one engine, for example. In some aircraft, there will be two intakes and two engines and so on. So this is called a viaduct intake, like our Indian Tejas aircraft, the light combat aircraft. So we are interested in this flow, that flow comes in through two of these limbs and they feed one engine. So at the engine, there would be combustion taking place. So the pilot puts in a throttle setting. So there will be very high pressure and temperature inside the engine. So you can imagine the pressure here is very high at the end of the intake. So I mean at this junction of the intake, the pressure is very high. So when you are designing an intake, what you want to know is that as you increase the pressure, what happens to the flow? If the pressure is too high for a given ambient pressure, you can imagine everything is going to come out. So this intake is not going to be able to sustain all the contents inside the engine, the air and the fuel. They will actually be thrown out of the intake. So you don't want that. So you want to design an intake which can work for very high back pressures. So we set up the problem. I'm not going to go into the details. So this is the back pressure ratio. This is the side slip. And just to show you what happens. So as you increase the back pressure, initially you get a very nice flow. And at some situation, you could get the flow unstarts. That means the engine actually extinguishes, it flames off. And that's no good. So we can simulate all those situations. So this is the buzz instability, where the shocks go back and forth and create a buzzing sound. So that's the buzz instability. I think I have run out of time. Maybe what I'll do is I'll just show you some animations of a different kind of an air intake. So this is a ram jet aircraft, a mixed compression intake, and show you some animations of maybe a buzz instability. Yeah, you can look at this one. It's a buzz instability. You'll see the shock waves. They will go back and forth. You can see that pulsating motion. Okay, so that's not good. So effectively, what will happen, because the engine is getting a mass flow rate that behaves like this, it's varying in time. So the thrust produced by this engine also varies with time. So imagine if you are a passenger sitting in that aircraft, then you will see your engine is producing thrust which changes with time. So you'll not feel good about it. And additionally, if the frequency matches the structural frequency, then you can have a failure, and that's no good. So this is an example of a little buzz. You can have something called a big buzz, which is a massive oscillation, as you can see. Okay, shocks going back and forth. You could have another situation where you have little buzz initially, followed by big buzz. So if you are patient, you will see a big instability coming up. There you go. Okay, so I'll stop here. Anurag, I finished my 1 hour. I'll be happy to answer any questions. And Thank you very much.
Okay, thank you, sir. Very interesting and nice presentation. So now it's time for open for question answer session. So anyone have any question, just ask.
Hello, am I audible?
Yes, you are audible.
Hello, sir. So I'm Pranil from IIT Guwahati. So I have just one question. I think in one of your slides you were showing that how wingtip vortices are generated on that cricket ball. So in the cricket ball, the wingspan, I mean, like for aeroplanes compared to aeroplanes, the span is much smaller. So these wingtip vortices, do they interact? And if they interact, what happens to like parameters like drag or lift and other hydrodynamic parameters?
No, great question. So, so Pranil, you're absolutely right. In a cricket ball or any lifting body, there will be wingtip vortices. So you saw frisbee has wingtip vortices, and cricket ball has.
Right.
Everything will have. So, do they interact with each other? Yes, they will interact, but that interaction will produce some instabilities far downstream, not in the near wake. Okay. And just
Okay.
like in an airplane, they will produce a drag. So they will produce an induced drag, and they will reduce the lift because the flow has leaked. But you can't help
Okay.
it. You can't put winglets or anything in a cricket ball. I mean, that's just how it is. So that makes the sport even more interesting. One aspect of
Okay.
these wingtip vortices is that they have an acoustic signature. They produce noise. So I think when fast bowlers
Oh,
they deliver quick bouncers, which will whiz past the ears of batters, it will produce some
okay.
psychological impact. These wingtip vortices will produce a buzzing sound and probably scare the batters. Uh,
Oh,
that
okay.
that I think is an aspect that is not pointed out too well by people. I think because they don't understand these vortices.
Okay. Okay. Thank you so much, sir.